Hello again. This talk actually, let me mark the time. This talk actually comes in two parts. So here is the first part. This part is called Minimum Time to Wake Up, which you can pronounce Me Too, or METAU if you like. I thought that was a nice acronym. And this is, at NAVAC we're all about, as I say, navigating towards your anesthesia targets. So this is something that I would like to propose to help you guide anesthetics. And so it's different from end-tidal volatile concentration monitoring. It's different from target-controlled infusion. It's a slightly different way of thinking about the administration of the anesthetic, how to maintain it stably, and how to wake the patient up. All synthesized into one number, the minimum time to wake up. So what are we going to talk about in this? We're going to talk about pharmacokinetics, because obviously that's essential to all drug administration, pharmacodynamics, how the drug works on the body. Going to briefly mention target-controlled infusion, which I'm sure many of you love, but as I'm sure you're also aware is not allowed to dumb Americans who are not to be trusted with target-controlled infusion, and therefore we don't use it, we can't use it, it's never been FDA approved. And then we're going to talk about this idea of minimum time to wake up, which I came up with as potentially an alternative to TCI that would be approvable in the US, but I think has some nice features that you might like as well. Now, I'm mostly going to talk about intravenous kinetics for this, but it does work with volatiles as well. Now, when we train our residents, I think we train them at my hospital. I think to begin with, we train them in quite a brutal way. We just tell them, do this. We want this out. When you see X, you do Y. We whip them and beat them, and we just program them, and that's how we get them. So there's a little bit of feedback. And that's how we first train them. And actually that's quite reasonable because that's how NASA trained monkeys to fly spacecraft in simulators, negative conditioning, do the task or I'll beat you. But that is sufficient to let a monkey know how to work the controls in a spacecraft. So that's how we treat the residents as well at the beginning. Okay, so when we are setting up a TIVA with a resident, okay, let's engage this case. So monkey enable, here's the resident pressing the buttons. They don't really understand, but we tell them that we want approximately these numbers. This is what we do as a standard for a TIVA. You may have slightly different numbers that you use in your mind, but some amount of propofol, some amount of remifentanil, some neuromuscular blockade. Remember to make sure that that IV line is intact and isn't dripping on the floor, and don't run out of drugs. And that's the advice we give to residents, or the command that we give to residents. Now, consider this. If that is the starting dose of all these drugs that you begin with, some of those patients may get a low BIS score or may become hypotensive. So you have to turn those drugs down. Some of those patients may not get a low enough BIS score, their BIS may still be too high, so obviously you turn the drugs up. Yes? Of course. Now, when you look back retrospectively, what you will then see is that the patients who are on the lower doses actually had the highest effects, and the patients who had the higher doses actually were getting the lowest effects. And that is what Dr. Snyder was talking about. That's the inversion paradox. So when you say, well, it can't be that way, maybe it's that way. No, it must be that way. It absolutely has to work that way. He's completely correct. That's the effect of titration on drug response. It also means when you see a paper where they are trying to make an algorithm that would mimic the behavior of an anesthesiologist, and it's trained on retrospective clinical data, sometimes they make the error of forgetting that there was an anesthesiologist there at the time. So what the algorithm is learning is not what an anesthesiologist should do to control the patient, but what they're in fact seeing is the vital signs that were already modified by an anesthesiologist. And I would suggest that that is the wrong data set to be training a machine learning algorithm against. And yet you see that mistake all the time. Now, how do intravenous kinetics work? So if we're not just going to be monkeys, how are we going to be smarter about administering drugs? So you give this is the 3-compartment model. Presumably you learned this as part of your basic education in anesthesiology. So you administer some drug, there's a central compartment, the drug redistributes and eliminates according to these terms that are rate constants that govern how the drug moves between these different compartments of the body. The compartments aren't real, They're just mathematical conveniences, but it happens to model pretty well. And all the drugs have propofol, remifentanil, fentanyl, all have different sets of numbers. So different effective compartment sizes and different constants that control how the drugs move between them. That's your basic 3-compartment model. And from that, you can generate these equations. I know this looks horrible, but this is essentially the rules of the game. So this shows how the drugs move between different compartments. So then, depending on what you want to happen, you have different starting conditions, different goals in mind. You can choose how you administer the drugs, and it either shows redistribution, or if you do TCI, you want the concentration to remain the same, and that allows you then to decide what your dose is going to be, so you control the dose accordingly. Now, so you can solve these equations to get an equation then for what you should do, and target-controlled infusion is one of those. I was going to show that more, but then I realized that it was a bit complicated. And then 2 days ago, I was at Leiden University, and as I was walking around near the horticultural gardens, I found this graffiti. And that, in Dutch, I'm told at the top, says, how much is there of the medication remaining in the body? And so there is a particular solution of that pharmacokinetic equation for administering tablets, and there's your toxic and therapeutic effects. So you probably thought that Banksy was clever, but that's the kind of graffiti they have in Leiden. So it's not that complicated at all for certain effects. Now, once you have the concentration in the body, then you have response surface models, and you can come up with an effect, or you can predict an effect based on what the concentrations are. So, is there another way to do this? Well, I have some software. And this is my gift to you all, it's free to grab. You can download it into your browser right now. It should work, hopefully it worked this morning. If you have a browser, you can go to bas.bwh.harvard.edu on a laptop or a desktop computer. BAS stands for Brigham Anesthesia Stimulator. BWH is Brigham and Women's Hospital, where I work. Harvard is Harvard, and that's the address. And it will download and run this software in the browser. And you can administer TIVA using that. So you can give mixed infusions of propofol, remifentanil, neuromuscular blockade. You can simulate the turning on of volatile agents, so you can have a mixed intravenous and volatile anesthetic. And it will make predictions about what the BIS would be, whether the patient will respond to stimulus, what the effect of the opioid is. But most importantly for this is that it will calculate this green number and this green curve, which is the minimum estimated time to wake up. And the minimum estimated time to wake up says, if I turned off all the drugs right now, how long would it take this patient to wake up? So how fast can I wake up from this anesthetic naturally if I don't use any reversal agents? How deep am I into this anesthetic? Because this is the problem I have with the residents, where they don't turn down the drugs, and we get to the end of the case, and they turn off the medications, and then we're still going to be asleep for 45 minutes because they've failed to understand any of the kinetics at all. But the nice thing about minimum estimated time to wake up is it shows you how the drugs will accumulate over the course of the case in the context-sensitive half-time, so that if you don't turn the rate down and don't act as if you're a target-controlled infusion, you will completely over-anesthetize the patient. So maintaining a stable minimum estimated time to wake up gives you, I think, a very stable anesthetic, and also helps at the end of the case when you're trying to turn off the drugs and get close to wake up. So now there's less surgical stimulus. You want to turn off the drugs at some point, so you have a nice descent, and then you hold just above the point where the patient is going to wake up, where you're 2 or 3 minutes away from wake up. So then when the surgeons are actually done, you then turn off the drugs completely, bang, you have a really crisp wake up, and you look professional. And that is what I want my residents to do. And I was always trying to find one way to summarize that idea. And this way of just a time remaining in the case, I think is a very clean way of doing it. So you can play around with that and see what the green trace does in terms of estimated time to wake up. Why this? Well, I don't think we've looked at it this way, but how deep into this anesthetic is a nice way to think about an anesthetic. You could also think of it as like the calculated anesthesia remaining if you turned off all the anesthetics right now. That curve is drawn in real time, so as you adjust the propofol and remifentanil concentrations, the curve will move around on the screen as you do it, so you can see exactly where it's going to go. It also avoids the two problems with TCI that have blocked it from being introduced in the US, which is that it doesn't try to control the pumps by itself, it just advises you, and it doesn't actually depend on saying what propofol concentration you're targeting, because we know that even with the most recent models, like the Elevold model, there's still often quite a considerable difference between the propofol concentration the device is targeting and the actual propofol concentration if you draw it out of a vein. And the FDA has always found that very, very problematic. I don't think it matters clinically. You guys seem to do fine with it. But that has blocked it being introduced in the US. Minimum time to wake up doesn't estimate that thing that is demonstrably inaccurate, so it avoids that regulatory barrier. So that's the idea. And this was just accepted in Anesthesia and Analgesia, so you should be able to read about it in more detail. Now, the other thing that you asked me to show you is an idea about alternative mechanisms for controlling anesthesia machines. So, what are our problems with current interface systems? Well, most of our interface systems for interacting with anesthesia machines still involve buttons and dials, maybe, if you're lucky, touchscreens. So this is a little bit behind the cutting edge. I mean, I understand that devices have to be robust, but it does seem like we're kind of lagging behind where the rest of technology is going. And there are problems with this, because when you have to touch the machine in order to operate it, you have to be within arm's distance of the machine. You also have to be able to touch the machine, which possibly you can't do if you've got sterile gloves and you're putting in a big line or doing a block. You can't touch the machine without contaminating yourself. So then you need someone to touch it for you, even to do the simplest things. Well, wouldn't it be easier if you could just ask the machine to do it for you? So why not have voice control for our anesthesia machines? This is already commonly present in our phones. It could reduce contamination effects. You don't need other people to do things for you. There's ease of use. You can go and maneuver around the patient to put in an arterial line, ask it to check the blood pressure, it will do that. Wouldn't that be easier? So how hard would it be to have voice control of an anesthesia system? So we decided that we would set out and build one. So here's the idea. So at the bottom here this is a hand control for a GE anesthesia monitor. So there's buttons on the panel of the machine, but they also made a remote control for it. Now, this is the kind of remote control that you used to have on televisions in the 1980s, if you're old enough to remember that, where the remote control was really on a long wire across the room. So you'd have the TV in one corner, there'd be a wire, and then you'd be your dad holding the controller sitting in his chair. So it's not a very remote controller, but it is a separate control panel from the main control panel, and it will respond to it. The advantage to this is you can buy these on eBay for not much money, just like I bought my BIS monitor on eBay for $100. So these only cost $20, $30 if you can find them on eBay. And you can take them apart. So here are the pieces. There's the remote control from a Solar 8000. There is a Raspberry Pi 4 single board computer. There's an interface board that I built, and then stuck on the top is a conference microphone. And this is this. So I'm going to pass this around so you can all have a look at it. It's all held together with glue and rubber bands for the prototype. So if you break it, don't feel too bad. I can just put it back together again later. So this connects to the anesthesia machine, and you can talk to it. And it also, you do need internet connectivity for this. So this is a controller. It usually has a knob on the top, which you turn to control the screen, and it has buttons that you push. And when you interact with the device, you create electrical connections. So if you want to make the blood pressure go, if you want to cycle the blood pressure cuff, you can, on the controller, just press the go stop button here. And then this is wired inside like the keyboard of a PC, where there's rows and columns. And you make a short circuit between the row and the column. So if you press go stop on the controller, it makes a short circuit briefly there. and that's a button press. That's how it knows that you pressed that button. You just have to make a short circuit between the row and the column. Well, that's actually quite easy to do. You just have a little electrical switch, and then with the computer you just tell it to enable that switch, and then the controller thinks its button's been pressed, even though you actually made it happen electronically. So that kind of short circuit is easy to make happen. So how would this work for anesthesia? So these are the steps of anything that does voice control. So there's a wake word, it listens to you, it processes it. There's this idea then of transforming it into an intention and then simulating the action. So say I have 5 minutes left. I say, hey Siri, start a timer for 5 minutes. Should I do? No, okay. So there's the awake word, which is hey Siri. So usually 3 syllables and kind of distinctive. Alexa, that's 3 syllables. Hey Google, also 3 syllables. So you need a wake word. I was interested, the head of our department is called Leroy Van Dam. I kind of had this idea that it would be nice to, he's unfortunately passed from this world. I kind of thought it might be nice to summon his spirit back from the netherworld to, help residents out. So let's imagine that the wake word is hey Leroy, which is also 3 syllables. So the computer listens until it hears that wake word, and here he is, looking disgruntled at coming back from the afterlife to cycle blood pressure. So, hey Leroy, and now we start recording, we listen for what comes afterwards, cycle the blood pressure. Okay, so once you stop speaking, that phrase, cycle the blood pressure, goes off to the cloud, and it gets converted into text. Cycle the blood pressure. Okay, does this match an intent? Okay, so our intention, when we say cycle the blood pressure, is to check a blood pressure with the cuff. We didn't have to necessarily say cycle the blood pressure. We could have said, what's the systolic pressure? Check the blood pressure. We could have said, is the patient hypertensive? All of these speech commands convey the same intention, that what we actually want to do is start the non-invasive blood pressure cuff. So we're going to listen for a wake word, record the actual words that we said, convert those into a written form, decide what intention that indicates, and then simulate that action on the controller. So make the controller think that one of its buttons just got pressed. So this is how you build that. So this is the inside of at the bottom is the inside of the controller, and this is where the keyboard hooks up, this is where the knob hooks up, and you can just take wires and connect up to those. And then electrically, you can make the controller think that you operated it, but actually it's all being done by the computer, which is listening for sounds and then determining what actions you would want performed. The neat thing here is that now you don't have to reverse engineer the interface to the machine, because you can just trick the controller into doing the actions that you want. So we've actually saved a lot of effort there. So we ran this with a group of 45 residents and attendings in our department, and it seemed to work very well. People liked the idea of having a controller that they could talk to. There wasn't any difference in preference with the age or experience of the anesthesiologist or the resident. They all seemed to enjoy using it. And all of our faculty, of course, are fluent in English, since we practice in Boston, but there also didn't seem to be any particular dependence on where people were from in the world or the pitch or gender of their voice. It seemed to work pretty nicely for everyone that we tried it on. So what we wanted to, we then asked the anesthesiologist what else should it do. They wanted it to do almost anything. Like, could it change the pumps for me? Could I use it when I'm doing blocks to change the depth of the ultrasound? Can it zero transducers? All of these things potentially can be done if you can hook up this device to that piece of equipment and operate it. So it's easy once you come up with a new intention that you want to implement, then you just figure out what the actions are and how you would wire that up to the device. One of the reasons for doing this is I don't think anyone's going to buy one of these from me, but I think it would be nice if manufacturers would offer voice control to us. And one of the ways I think to try to make that happen is to just show that it is possible, and then hopefully that will become something that their engineers might also wish to want to offer. So that's Alexa cycle the blood pressure. And a lot of everything I've shown you here has really depended on reverse engineering and taking equipment apart. So if you're a resident or if you're junior faculty, what I want to say is there's a lot of secrets and fun hidden inside the equipment. So if you want to be a technologist, don't stop at the front panel of the equipment. If you stop at the front panel, you're not really a technologist, you're kind of a knobologist. You know, you're really good with the knobs and dials. Get inside the equipment if you want to find out its secrets. Because I think you have to not be afraid to smash your instruments.